another 5 minutes. So are you here? Can you write in the chat if you are ready? However, I guess you can see my desktop. So here, as you can see, there is the agenda of today. Today we have quantum algorithms, part 1 and part 2. So we're gonna have a deep dive into the ocean of quantum algorithms, and it's gonna be more demanding probably because there's some mathematics involved. Then after lunch, we're gonna see Qiskit, which is the quantum computing library in Python that we already seen something about it yesterday with Marco. And you can use Qiskit to program quantum computers. And then something about quantum error correction. Okay, so let me say that in the home page of the course, you have the material from yesterday, and you can also download what you're going to see today. So it's day 2. Okay, then. Okay, let's start with this lesson. So my name is Riccardo Mengoni. I'm a member of the Quantum Computing Lab in Cineca. My background is in physics. And I did my PhD in quantum machine learning, and it's been a couple of years that we're working inside Cineca. This is the Italian high performance computing center, and we work in quantum computing. Okay, what we usually do. Okay.
Riccardo, so just a moment.
Yeah.
Good morning, everyone. This morning we have also Lorenzo Locutto and Marco Maronese.
Okay.
That will be teachers for Friday, for the lesson of Friday. So Lorenzo and Marco, are you here? You want to introduce yourself? Hi, Lorenzo. Good morning.
Hi. Okay. Brief presentation for myself. I currently work at IIT in Genoa, and I had my master degree in Milan in theoretical physics. I'm currently studying data science, and I will be presenting a brief lesson about quantum machine learning on adiabatic quantum computers. And that's it. Thank you.
Thank you, Lorenzo.
Thank you.
Thank you for being here.
Hi, I'm Marco Maronese.
Good morning, Marco.
I have a master degree in theoretical physics in University of Milano Bicocca. And now I'm doing a PhD in data science and computation. My research field is focused on simple quantum computing or gate model quantum computing. So see you on Friday for the lesson of quantum machine learning. Thank you.
Thanks a lot. Okay. So sorry for my interruption.
No, no problem, no problem.
And, then we can start.
Yes.
Thanks a lot.
Bye. So let's go on. So yeah, I was saying something about our quantum computing lab. So what we do is we do research. We collaborate with research universities, industries, and also quantum computing startups, and we also provide internships, courses like this one, and we also organize every year in December the high performance computing and quantum computing course, and this is the link to our website. So if you're interested in any of these things, please drop me a line. Here you have my email address. Okay. So I think we are okay, almost 50 people. So okay, we can start with the recap of what we've seen yesterday. Okay, something about linear algebra and the postulate of quantum mechanics, so the basic formalism. So very briefly, because you have seen this yesterday. Okay, the first thing that you need to have in mind is this Dirac formalism for quantum mechanics. So you have vectors. Vectors are usually represented in this way. So we have cats, so with this bracket like here. Psi is the usual way you represent quantum states. So what does it mean? It's a vector where each element is a complex number. The bra is like the adjoint or the transpose complex conjugate. So which means that it is just you put everything on a row and you complex conjugate every term. So this means the bra. Okay, so how you do scalar product? Scalar product very easily. It's row times a row by column multiplication. Okay, matrix multiplication. So you multiply phi1 complex conjugate times psi1 plus all the other pairwise terms. Okay, and of course you get something that is a complex number. This is the scalar product. You can also introduce a norm that is the square root of the vector scalar product with itself. Okay, then we have an outer product that is something, so it's like the opposite. So you multiply a column with a row. What does it mean? It means that if the two have dimension n and n, at the end you get something that is a matrix of dimension n times n. Okay. How this kind of matrix is constructed? So you multiply the first element with the first one.
Ok, infatti va bene.
Sorry, can you switch off the microphone?
No, ma va bene. Perché ti giuro che c'era.
Okay. Okay, so you get something that looks like this. Okay, this is trivial to understand. Okay, psi1 times all the elements, and you get this kind of matrix here. Okay, so there is the tensor product. So these two are vectors. Tensor product, you multiply each element of the first vector with the full vector of the second one here. Okay, so of course you increase the dimensionality, and what you get when you multiply two vectors of dimension n, you get something that is n squared. Okay. Okay. Oh, this is very important. So this is the compact form, a compact way of writing this tensor product. So you have psi tensor product phi. It's the same as writing it in this way, so without the tensor, without explicitly writing the tensor inside here. Or you can also write everything into the same cat state and write it in this way. Okay. I think, okay, are you with me so far? Can you write something in the chat? Is it okay so far? So I think this is linear algebra. Most of you have a scientific background, so it's going to be quite okay. Okay, perfect. So let's start with the postulate of quantum computing, again, very briefly. So the first postulate concerns the unit of information. Now, you know that classically the unit of information is the bit. So it's something that it's either 0 or 1. So you can write 0 and 1 as vectors in this way. Quantumly, okay, to a closed quantum system is associated some Hilbert space, and a state of the system is represented by a vector. So this vector, the simplest system, is the one associated to the qubit. Okay, so the state of a qubit is something that looks like this. So it's alpha. It's a linear combination of the bit states. Okay. So a complex combination, I mean a linear combination of complex numbers. So alpha and beta are complex. No? You know that, okay, the space of state in the case of a qubit is C2, of course, because alpha and beta are complex. What else? Since alpha and beta are probability amplitude, so they, since their norm squared, the sum of their norm should be 1, because I mean, the norm square is a probability, so the sum of all probability, of course, is equal to 1. And you can also parameterize, you can also rewrite basically this state here in this way, using theta and phi, as which belong to these two intervals, okay? And you can easily check that this, if you square these two, if you do the modulus square of these two and you sum them, you get 1. Okay, because this goes away and cosine squared plus sine squared is 1. No? Okay, and since you can write this, you can parameterize it with theta and phi. You can also visualize the state of a qubit in this way. So it's a point on this surface. No? A state of a qubit could be any point on the surface of this sphere. No? While classical state 0 and 1 are just the north or the south pole. Okay. The second postulate concerns a composite system. What does it mean? It means considering n bits or qubits. Okay, classically, when you have n bits, the state of n bits is either one of these. The state can be one of these possibilities. Okay, you can have n bits all in the 0-0 state, or some of them in the 1 and they are in 0, or all ones. Okay, just one of these 2 to the n possibilities. Quantumly, as you know, okay, the state of the space of state of composite system is the tensor product of the subsystems. So what does it mean? It means that you can write the state of n qubits in this way. So it's a linear combination of complex coefficients of all the classical, okay, states. Okay, and this is your quantum state. Of course, as we've seen before, the sum of AI modulus square is 1, okay, because again, they are probabilities. Okay, what does it mean in terms, what is the consequence of this? The consequence is you can have two kinds of states. States that can be written as tensor products, so where you can separate all the states associated with the subsystem, with the single qubits, okay, and these are called factorable product states. And there are also states where you cannot write in this way. Okay, and these are typically called entangled state. Okay? There is no way you can manipulate the state and write them in this way. So an example are the bell states, okay, like this one that we are gonna see a lot in this lesson. Okay, so for example, take the first one. There is the way I can separate the first qubits, which is this one and this one, from the other in a way that so I cannot separate them with some tensor product. Or, okay. Okay, so these are entangled states. Okay, there is some question. Okay, what's the physical interpretation? I mean, it's not like a physical interpretation, I guess. It's more a way of visualizing it. So again, you, I don't think, I mean, as far as I know, it's just a way of visualizing. There is no physical interpretation. I mean, psi, phi is the quantum state, and it has some, okay, it's a superposition of 0 and 1, so which means that when you measure it, you can get 0 and 1 with probability alpha square or beta square. And yeah, you can also write alpha and beta in this way. So with cosine and sine and e to the I phi. Phi is this angle here. Theta is this other one. It's just a visualization, so there is no physical interpretation to this. Okay, so let's go on. Yeah, yes, exactly. So phi adds a complete phase. Yeah, otherwise everything, I mean, yeah. Okay, they're real numbers otherwise. Okay, so state change. So the third postulate is state change. What does it mean? It means that how you can vary your state. Okay, classically, you can vary the state of bits by applying logic gates. Okay, quantumly, the evolution, so you can state change in a closed quantum system is described by unitary operator. So the evolution in time of your quantum system, of your quantum state psi, is described by the Schrödinger equation, whose solution is this one, where e to the minus I ht, where h is something that is called the Hamiltonian that defines the energy of your system, so how it, and also describes how it evolves in time. And this is a unitary operator, so everything is unitary. Okay. Okay. So so quantumly, so you can how can you realize these unitaries? They are quantum gates that we have seen yesterday. So okay, let me clarify another thing. So for the qubit, now the state of a qubit is a point on the surface, so you never go inside. So it's some point on the surface, so because the norm is should be 1. So you stay always in the surface when you have a single qubit. Okay. Okay, then measurement. The fourth point, the fourth postulate is about measurement. So of course you know that when you measure things in a classical world, you get a result, you get an outcome with certainty. Okay, so if the state of a bit is 0, then you measure it, the outcome, okay, here we get the problem, but yeah, the outcome will be 0, of course, like in the one case. So measurement do not affect the state of a bit. quantumly is the opposite. So measurement returns the state of a bit. So you don't have access to the quantum state, but measuring it, you collapse it to one of the two bit states with some probability. The probability is alpha squared, modulus squared, and modulus beta squared. Okay. So the measurement, in contrast with what happens for classical bit state, so measurement affects the state of a qubit that collapses to one of the two possibilities. Okay. Okay then. So what happens in more mathematical terms? So you can define an observable that is like a quantity that you want to measure. And every time there is a quantity that you want to measure, it is associated to an Hermitian operator, so some matrix. This matrix will have some eigenvalues and eigenvectors, like defined in this equation here. And the measurement of this observable, of this quantity that you want to measure, returns the eigenvalues, so the O of I. The probability of obtaining O of I as a result of the measurement is the scalar product of psi with this eigenvector of I, modulus square, of course. So the state after the measurement changes from psi into the eigenvector of O. So from psi to O of I. So it's exactly what we've seen here in a more generic term. So, okay, before you have superposition, when you measure, you usually measure something that is called the zeta operator. And so in this case, O, so the observable is zeta. And what you get is 0 and 1 that are the two eigenvectors of the zeta operator. Okay, with some probability, it is exactly 0 scalar product psi, which is alpha squared, modulus of alpha squared. Okay, it's exactly the same in a more generic way. Okay, so are you with me? Do you have questions so far? Because then we're gonna see these kind of things a lot. Okay, let's see, there is some, yeah, okay, yeah, quantumly, so you can write the quantum state in this way. So this is, it's something that is not classical. So before the measurement, okay, the measurement, so it's not, a statistical mixture. So it's not something that like you don't know. So it's not your problem. It's not that you don't know which is the state before the measurement. It's the other thing is that before the measurement, the state is not, let's say, defined classically. Okay, it's something purely quantum. Okay, it's not like tossing a coin. So before, let's say, you toss a coin, and before you look at it, you don't know the measure, you don't know the outcome. So that is a statistical mixture. Okay, before you don't know, but it's your problem. It's not something that it's due to your non-complete knowledge of the system, which is the coin, no, that rotates in the air. Okay. Here instead it's something completely different. It's a quantum superposition, so it means a quantum system whose state, whose classical, who is in a combination, linear combination of classical states. So it's not a statistical mixture. Okay. So let's start with quantum algorithms. Yesterday we have seen something about this. So okay, tell me, write me in the chat if you are okay with this so far. Are you Are you okay with the postulates and the quantum and the linear algebra and everything? It's okay. If you have questions, please ask in the chat, because I actually have 3 monitors and I'm looking at everything. Okay. So don't hesitate. Okay, I can go back a little bit if you want, because there's okay, wire metering operator. So everything, I mean, everything in quantum computing is Hermitian because let me see if I can get here something. It's an Hermitian operator, okay, because well, this okay, I don't remember right now, but Hermitian means that the H, I mean that the operator is equal to its it's equal to its adjoint. Okay, and the Hermitian operators, oh yeah, okay, they have real eigenvalues. Yeah, because this eigenspectrum is real, so energy is real, yeah, momentum is real, so they, yeah, exactly, the observable need to be, yeah, real values. Yeah, that's true, for sure, yeah. Okay, thank you. Okay, let's go on. So with quantum algorithm, quantum circuit, okay, it's quantum algorithm or quantum circuit, they are interchangeable, okay. Quantum circuit with n inputs and n outputs, qubits, is defined by a unitary transformation, okay. You can write the set of unitary transformation as u to the n, okay. 2 to the n because they are basically matrices, unitary matrices of dimension 2 to the n, so 2 to the n rows, 2 to the n columns. A quantum algorithm, so it looks like this. This is a quantum circuit. So for gate model quantum computing, this looks like this. Okay, so we have initialization and quantum gates, and then measurement. Okay. So let's briefly review the quantum gates that we have seen yesterday. So you have single qubit gates. So a generic single qubit rotation is a matrix that can be written in this way. So we have cosine theta over 2i, where I is the identity, minus I sine n times sigma. So this is just to n is just a vector that selects the Pauli matrix. Okay, so you can have sigma x that is basically is x, so it's the bit flip matrix, so the knot matrix. You have the y, sigma y is this one, where you have minus I and I on the of diagonal terms, and we have z zeta, so it's 1 minus 1. So the nice thing about 1 is minus 1 is that, as you can see, the eigenvalues are 1 and minus 1, and the eigenvectors are 0 for this eigenvalue here, and minus 1 for the eigenvalue for the eigenstate 1. Okay, as we've seen before. Okay. So one of the most important single qubit gates is the Hadamard gate. Okay, it's defined in matrix form in this way, and is usually represented in this way in a circuit. What's the action of the Hadamard gate? If you apply H, to the zero state, you get a superposition of this way with the plus. So it's an equal superposition because we have the 1 over square root of 2 that multiplies both. This is also called a plus state. And if you apply Hadamard to 1, you get this other state with a minus, and in fact it's called minus state also. So this is going to be used in the future. So I suggest you maybe to have something, a paper in front of you and a pen, and write this matrix here, or the action, okay, of H on the paper. So I'm gonna do it as well. Probably, yeah. I have it here, so I can write H of 0 equals 0, or H of 1. No, sorry. Equal 1 over square root 0 plus 1, and 1 over square root 0 minus 1, because H is equal to 1, 1, 1 minus 1. Okay. I suggest you to write something like this in front and have it in front of you, because it's important for the rest. Okay. So what we have here is a phase gate. Phase gate, it's look like this. So you have e to the I5. So you add a phase when the bit state is 1. So when it's 0, you add nothing. When it's 1, you add some phase. Okay. So of course, when you have a state like H, and then a phase gate, you get a phase only. So you get a first superposition, and then a phase only on the one part of the superposition. Okay. Swap gate. Okay, this is a 2-qubit gate. So swap basically is something that looks like this. So if your initial state is zeta 1, zeta 2, and you swap them, what you get is you get zeta 2, zeta 1. Okay. Use the matrix form like this one. Of course, you see here now that if they were here and here, it was the identity. You just swap it. Okay, you just exchange. Okay, the two, and the symbol for the swap gate is this one. Other 2-qubit gates, so the control knot. So the control knot is this qubit here, is this matrix here. So basically you have the identity, and this gate here is the X gate. Okay, this the 2 by 2 in the bottom right corner. Okay, is the X gate. So that's why it's a control knot. Okay, this is the way of representing it in the circuit, and this is the action. So whenever the first bit or qubit, okay, is in one state, you flip the second one. So for 0, 0 stays the same, also 0, 1 stays the same because the first is in 0. For 1, 0, 1, 1, you flip the second qubit. Okay, so the first one is 1, the second is 0, then the second one becomes 1, and the opposite in this case. Okay. In general, you can have some control unitary gates that look like this. Okay. Control unitary gates act in this way. So the zeta 1 is unchanged, and you perform a U operation on zeta 2 depending on the value of zeta 1. So usually you can write it in this way, because if zeta 1 is 1, you get a U that is applied to zeta 2. If zeta 1 is 0, it's like U to the 0, and always is, which is always the identity. No? Okay. So for example, we have the control phase that is exactly of this kind. So it's you play the phase whenever zeta 1 is 1. So, and the matrix form, this is shown here. So again, is the identity matrix in the upper, in the 2 by 2 up left corner, and then here you have the phase gate. Okay, you can split the matrix in this way, and this one here is the way you can you represent it. Okay, you have the Toffoli gate. Toffoli is basically a control not gate. So you change the value of the third bit if the first 2 bits are 1. Okay. And yeah, the action is this one, and the way of representing it is this shown here. Okay, now let's talk about universality. So what does it mean? It means that in order to so what do we want? We want to find out which is the smallest set of gates, of unitaries, of simple unitary gates, thanks to which we can build any unitary on m qubits. So, and this is okay, the definition. So we can exactly build any unitary u on n qubits, so, which means that the dimension of the u matrix is 2 to the m times u to the n. Okay, yeah. 2 to the m columns, 2 to the n vectors, rows, by means of single qubit gates and control not. So, and this is an exact set, so which means that you can exactly build any unitary, okay, with U2, so all the single qubit gates, single qubit unitaries, and control not. Okay, so a single qubit unitary looks like this, and the C naught looks like this. So, but usually it's okay when you implemented this in the hardware. Yes, it also means that yeah, you can. Yes, exactly. So any state can be achieved with the proper unitary. Yeah. So you can build any unitary in this way. So with this exact set. So every unitary for the qubit plus the control not. Okay, there is also the proof, but I'm going to skip it because it's quite complex. But okay, in more practical terms, okay, you don't want to, so you don't have access to the full set of unitaries associated with a single qubit. So what you can do also, you can get universality. So you can get universality means that this set here is universal because you can build any unitary. Okay, you can also get universality in approximate sense. What does it mean? It means that if I have 2 unitaries belonging to u to the u to n, and u prime approximate u within some epsilon, which is small but greater than 0, if the distance between the two is less than this epsilon, so it can approximate. So in this case, you say that u prime approximates u. Okay, where the distance, so between u and u prime, is defined in this way. So is the norm of this vector here, where you basically do the difference between the two unities, the two matrices, okay? And max over sigma, max over psi means you not only do the you have to apply this gate, that is the difference between the two, to all possible states, and you get the maximum norm that the maximum norm defines your distance. Okay. Yeah, of course. Yeah. So okay. Let me say. Okay, let me say with the next slide. So you can approximate any unitary. So you can build a unitary, but in approximate sense, approximate in the sense that we've seen in the previous slide, with a finite set of gates. Okay. The set of an example of this set of gates that can achieve universality in approximate sense is this one. So we have control naught plus Adamar that you already know. The S gate that looks like this is a phase gate, and a T gate that is a phase gate with pi over I pi over 4. Okay. So, and this is very useful. Okay, from when you, I guess this is one of the answers. Okay, when you want to build an hardware. Okay, because the previous one was a set which is hard to, so it's hard to get all the possible single qubit unitaries. Okay, but here you have a finite set. Okay, and you can achieve universality in approximate sense simply by means of this finite set of gates. And of course, yeah, it's I mean, probably then for certain, depending on the hardware, probably some. So this is not the only set of gates that achieve universality in approximate sense. So probably for one kind of hardware, it's easier to build some of them. For other hardware, it comes natural to have, I don't know, for example, the Toffoli gate, probably. Okay, so it depends. Yeah, of course, it depends on the hardware. And however, this is not the only set. There are multiple choices of sets that achieve this kind of universality. So you can choose, let's say, the best one for your particular device, and you have to be wise in this choice. Then, okay, so let's go with the basics, okay, of quantum algorithms. Okay, again, here, yeah. The first thing that I want to clarify is the following, shown here. So we know what's the action of H when you apply it to a single qubit. But what happens when you have n single qubits and you apply H to all of them? So usually the way you represented it graphically, okay, the way you represented it is this way, okay, which means that this sign here means that you're doing it n times. Yeah, okay. Okay, the Adamar is the one that we have seen before, and that hopefully you have written in front of you also. Okay, so you can also write the Hadamard gate in this way. Okay, the simple Hadamard gate. So what does it mean? It means that this is a different notation, but is the same as the matrix notation. Okay, if you have in front of you the Hadamard in matrix form, you see that they have 1, 1, 1, and just the last one is -1. Also here you have 1. The coefficients are 1, 1, 1, and for the last one is -1. What does it mean? It means that this term is associated to the first number, so the first element here in the matrix. The second one is the 0, 1. So these are also positions, okay, in the matrix. So the 0, 1 position is this one. The 1, 0 position is this one. The the 1, 1 position is this one here. Okay, so that's why this is a way of writing the Hadamard gate. It's maybe not trivial. I mean, it's not trivial, but you can see quite easily that when you apply hn, so h on n qubits, which means h tensor product with himself n times, you get something that looks like this. So it's a sum of all possibilities, all x and y's, belonging to 0i to the n, multiplied by -1 x times y. What does it mean? It means that only when the two multiply and you get 1 in the exponent, you get -1, like in this case. Okay, so here 0 times 0 is 0, 0 times 1 is 0, 1 times 1 times 0 is 0, 1 times 1 is 1. Okay, and that's why you get a -1 here. So this is a general form, and this is something that I suggest you to write in front of you. So I can write also here. So you have n is equal to square root 2 to the n, sum of x and y belonging to 0, 1 to the n, -1 x times y, x, y. Okay? Okay. Okay, let's go on. So what's the action of this h tensor n gate? When you apply it to 0, what happens is the following. So you get this scalar product here. So y scalar product with 0. This is 0 every time, except when y is equal to 0. In this case, it's a scalar product between 0 and 0, which is 1. So you usually define this with the Kronecker delta. So it's a function that is exactly 1 when the I and j are equal and 0 otherwise. And this is actually what happens here. So what happens is that y gets equal to 0. So also here in the exponent, we get x times 0, which means that this term is equal to 1. And we are left with the normalization, the sum, and x. So y goes away because it's 0, 0, 0. Okay, so we are left with just this sum here. Okay. Okay, let's you have also to keep in mind, okay, the action of the Kronecker delta. So whenever you have this kind of thing here, you get a Kronecker delta. The third part, the last part of the basics of the the quantum algorithm basics is function evaluation. What does it mean? It means that whenever, if you're given a function f that goes from 0, 1 to the n to 0, 1 to the m, then an algorithm that evaluates such function is given by a unitary UF. And the action of UF is the following. So you have 2 qubits, two bits. You apply U of f, and what you get is that the value of x, so f of x, is stored into the second qubit. Okay, so you get x for the first qubit that is that does not change, and y becomes ny plus f of x. This is the summation modulus 2. Okay, because these are 0 or 1s. X and y are 0, 1 to the n, so are bit strings. Okay. Okay, so before going on with the complex quantum algorithm, let me so write me in the chat if you have problems, or if you're with me with this thing. Okay, I suggest you to write this. Suggest you to write these functions here. So the action of Hadamard, because it's going to be important. So write me in the chat if you are with me. Okay. Okay, this is a definition, basically. Okay, so a unitary that realizes quantumly the function f is something defined in this way. So whose action is defined in this way. So where you start from a bit, which is, for example, 1, 0, you apply U of f, and you get again 1, and here you get y that is 0 plus the function evaluated in the value defined in the first bit. Okay, let me go back to the, okay, yes, sure. So this is the definition, okay? If you just try to write, okay, I mean, a function that is, that always give you 1 independently on the input x, okay? So this is gonna be, so I'm right, and yeah, try to do it yourself, okay? However, it's a definition of a unitary that evaluate an algorithm that evaluates the function, okay, in quantum terms. And so, which means that by changing x, you evaluate a different input, okay? You evaluate f in a different input, okay? With the multiple Hadamard gate, what happens? Okay, are you with me with this formulation here? I mean, I didn't derive this, but okay, no, it's just a general way, no? A generalization of this one. Okay, here. You have here the Kronecker delta, and this is okay, I think. Okay, so what happens? Okay, I'm gonna write it here. Okay, let me write it Okay, so whenever you have 0, so this becomes Kronecker delta y0, which is 1 when y is equal to 0 and 0 otherwise. What happens? It happens that, okay, then y becomes the 0, 0, 0, 0 string, okay? After this part. What does it mean? It means that if I go and substitute this here, you get -1 x times the 0 state, which is 1. Okay, so x, this is 1, as we said, because this is equal to 1. Okay, and then you're left, because epsilon is just a number, you get x, and this remains. Okay, is it okay? Okay, so I'm gonna go back to the previous, no, I'm gonna leave it like this. Okay, so let's okay, you need 2 qubits because in one you encode the input, so x is your input and y is your output. So that's why you need 2. So one is for the input, one is for the output. Okay. Let's start with the Deutsch-Josa algorithm. Okay, yesterday we have seen with Daniele the Deutsch algorithm, which tells you, we just it's about okay, but let's see the Deutsch-Josa, which is the extension of what you have seen yesterday, the Deutsch algorithm, to the case of where you have a string of n elements. So the problem is the following. Okay, we consider a function f going from 0, 1 to the n to 0, 1. So yesterday it was just a single bit. So it was n equal 1. Okay, this is the general case. Okay, this is the Deutsch-Josa problem. If f 0, 1 to the n goes into 0, 1, this is our function. And we don't know exactly how this function is done, but we know that, I mean, it's not important. Which is the function. What we know is that we know in advance that such a function is either constant or balanced. What does it mean? A function is constant if returns 0 or 1 for every input. So it's a constant. So whatever input you give it, whatever bit string of n elements you give in input to f, you get always the same result. Okay, you get always or 0 or 1. Okay, balanced is a function that returns 1 for half of the inputs and 0 for the other half. So, for example, when you have okay, let's say mathematically, you can write it in these ways. Okay, so A0 is the set of inputs that give output 0. A1 is the set that give as output 1. So if the function is constant, what does it mean? It means that you have either one or the other possibility here. So the cardinality, which means the number of elements in this set is equal to the full space, or for the other happens. Okay, so in this case, A0 is the full set of possible inputs, and in this case, A1 is going to be an empty set. In this other case, A1 is the full set, and A0 is an empty set. Okay, balance instead is the other scenario where they split the the full space into two halves. Okay, so that's why the dimension of these two sets is 2n minus 1, which is 2n over 2. Okay, so, and this is okay. Are you with me with this formulation? Okay, it's what we've seen yesterday, but to the n case. So if you are with me, try to ask these questions. So classically, okay, how many evaluations, so how many queries of the function are needed to determine with certainty if such function is balanced or constant? So you have like some seconds to think about it and write your answer in the chat. So how many times you want to evaluate a function in order to be sure that it is balanced or constant? So try to reason. So again, balance means you get half of the times 1 and half of the times 0, and constant means that you always get 0, let's say. How many times you want to evaluate f, which means how many times you want to calculate f for different inputs, in order to determine if this is balanced or constant. Yes, of course, when you select an x, that is your input, and you calculate f of x. Yeah, you know x and f of x. Yeah. You want a question with certainty. Okay. Okay, let me. Okay, I saw somebody that got it right. I think, yeah, Lucius got it right. So what does it mean? It's 2, so it's the half. So you have to evaluate the function on half of the possibilities plus 1. Okay. So since all the possible input strings are 2 to the n, we need to check on average half plus 1 strings. Okay, which means 2 to the s minus 1 plus 1. So basically, the concept is the following. Okay, consider. Okay, this is our function. Consider an input. Your input is x1. Okay, the result is 0. Okay, if the function is balanced, okay, and I'm very lucky, if I get a second input, which is x2, and I get a result that is not the one that I obtained with x1, with just 2 queries, okay, I get with certainty that the function is balanced. Okay, but this is the luckiest case. Okay, if I'm not lucky, okay, if the function is balanced, if I'm not lucky, I have to consider all the functions, all the I will have to evaluate all the inputs that give the same answer, and then the half plus 1 string is gonna be it's gonna tell me that okay, it's you were very not lucky. Okay, so you always got in the first half all the strings that gave a function to which you were so you were getting always the the input string that gave the same answer. Okay, so the half plus 1 is gonna resolve your problem. Okay. Okay, maybe it's not again clear, but okay, this is the question. So you have 2 to the n possible strings. Okay, in order to be sure, you have to evaluate half of them plus 1. Okay, because you don't know if you are just if you get always 0, you don't know if the constant the function is constant or you're just being not lucky. Okay, so that's why okay, this is the classical query complexity. Okay, let me. Okay, no, it's not clear again. Okay, let me do with an example here. Okay, this is easier with an example. So let's say that I have my function. I have my function, okay, and I evaluate it on x1. What I get is f of x1 equal 0. Okay, so my idea is that I don't know. At this point, I still don't know. x2, if x2 is equal to 0 again, could be constant or balance again. So you don't know, because maybe the next one, x3, is gonna be is gonna be 0 again. So you don't know. You don't know if I'm just being I'm just getting all inputs that belong to H0, but the function again is balanced, or I'm getting this because the function is constant. So you don't know. You still don't know. You are not. You're left with this question. You're left with this question until you reach x to the. I mean, not until you reach, until you get the first one. Okay, if you get if x of 55, I don't know, is 1, f of x of 55 is 1, then you know it is balanced. No, as soon as you get 1, you know it is balanced. Okay, but you don't know when this may happen. Okay, in the worst case scenario, this will happen when not at the 55, but when I am trying to evaluate the 2n minus 1 plus 1. I mean, no. In the worst case, I think it's the half plus 1, term. Okay, in the worst case. So of course, in the worst case, you have to evaluate, okay, this number of times. Okay, maybe it's a little bit more clear now. Yeah, sure. It's asymptotically is 2 to the n. Maybe it's a bit more clear now. Is it? Can I go on? So just probably yes, of course. The x are all different. Yeah. So okay, maybe we will better understand this afternoon with the with the example on Qiskit. Okay. Yeah, of course. Yeah, all x's are different. One example could be, I don't know. If I have, yeah, 0, 1, 0, 1, 0, 0, 0, 1, 1, okay? X belong to the set 0, 1 to the n, okay? So the x's are all different, okay? So when, so if you are lucky, you get, so imagine the function is balanced, okay? If you are lucky, you get the first, with the first x, you get an output 0. With the second input, you get an output, you get f of 1, f1. So this, so lucky x1 give you f of x1 equals 0. x2 give you f of x2 equal 1. Balanced. No? In the case of balance, okay? This is the lucky case. The worst case, so the case that is opposite to being extremely lucky is when x1, the function is balanced there. So x1 give you 0, x2 give you 0, and so on until x of 2 to the n minus 1. That give you f of x2 or f2 to the n minus 1. That gives you 0. Okay, this is the worst case. But then, if the function is balanced, you know that x2 n minus 1 plus 1 is gonna be 1. Okay. So in the simplest case, you just need 2 evaluation. In the worst case, you need 2 to the n minus 1. Okay. So this is basically the idea. Okay, perfect. Okay, so okay, this is classically. Okay, classically it's exponential, no? with the n. Let's go on. So the Josa algorithm proposes a quantum solution. Okay, the quantum solution is implemented by with this algorithm here. Okay, we have O applied n times, and so we have tensor n times. We apply h n times to the 0 state, like we have seen before. Here we have another register